Let's continue with the conservation of energy. And in this area, what I would like to discuss is flow work. It is a critical area to study. One of the fundamental areas of this is in a cylinder piston type situation. So here, within the cylinder, what I have is a gas. It's at a certain pressure. That pressure is acting against all surfaces, including the piston. And the cross-sectional area of that piston times the pressure will give us the force. That is, the force is going to be equal to our pressure times the area. Some Newton per meter squared times the area meter squared to give us our force in newtons. Work, by definition, is the force times the length. So if I'm applying a certain amount of force at this location and I move it down to location ch02, that distance traveled based on that force, which can vary with time certainly, will give us the total work. So our work will be the integrated value of the force times the distance, and that force can be replaced thermodynamically with the pressure times the area. The pressure will change as the piston continues to expand, so it does vary with x as well. And what we see in thermodynamics is always the work is equal to the integral of P dV. And the reason that we have it as dV is that the area, that area of the piston moving a certain distance will be the change in volume. And that's where we get the volume, or our dV, in our calculation. If we do have compression, then the change in volume is negative and our work would be negative. And if you think about it, you have to exert work on the piston in order to compress it. I stated that the pressure will vary as that piston moves. So what that relationship is between the gas pressure and the distance that the piston has moved needs to be determined. Frequently, realistically, that is not so easy to do. However, for most thermodynamic applications that we are dealing with, we can go ahead and assume that we have some form of idealized process that is happening, and that the pressure is uniform within the entire cylinder. And in that type of situation, what we have is a quasi-equilibrium process. We are taking things on their bulk type analysis rather than on an individual or micro scale process. Therefore, if I had a pressure gauge within that piston cylinder assembly and I measured what the pressure was at state 2, and as it expanded to volume 2, I could monitor what the change in pressure was as a function of time. The area under the curve is the work. Frequently in our thermodynamic processes and actual engineering problems, we can usually assume that the pressure times the volume raised to some power would be equal to a constant. If that is true, then we have a polytropic process. When the value of n is equal to unity, then just PV is equal to a constant. I get the following formulation, that the work is equal to some constant times the log of the volume ratio. So how do I get that? This is worth, deriving out. What do I know? I know that PV is equal to a constant. And if that's true, then I know that P is equal to the constant divided by V. Therefore, I can substitute this term into our P formulation. So now I have that the work is equal to the constant times the integral of 1 over V dV going from some state V1 to another state V2. The integral of 1 over V dV is equal to the log of our V2 divided by V1. So what happens when we have PV to the N is equal to a constant. This is the other application that we need to be able to do as a thermodynamic engineer. I think you can see then that the work is going to be the constant times the integral from V1 to V2 of 1 over V to the N dV. So before you move on to the next page, please go ahead and figure that out by yourself. What is that answer? You ought to be able to do that without having any additional guides. Rewriting this just a little bit, we have that this is equal to the constant times the integral of v to the minus n dv. And therefore, when we evaluate that, we have v to the minus n plus 1 over minus n plus 1. And that will be evaluated, at the v1 and the v2, and we still have the constant multiplying that. And this term can be reworked to the following. So that we have our P2 V2 minus P1 V1 divided by our 1 minus n power for any value of n not equal to 1. Naturally, if we are talking about some type of engine running at 5,000 RPM, you're going to certainly get non-equilibrium effects taking place. However, the initial assumption of saying that I am at a given pressure at state 1 to another pressure at state 2 is reasonable for first order estimates of the work.